In the last lesson for this module, we're going to talk about the uncertainty that surrounds even the best data collected using edge of field monitoring. Uncertainty is a part of any science, and so is change. They are both normal and necessary parts of the scientific process. The scientific process is an ever-evolving, continuous improvement loop that necessarily involves some uncertainty. Remember when we thought Pluto was a planet? We were all working with the best available science, and that best available science changed over time. The fact that science changes and has some uncertainty to it has led to some mistrust by the public. But in fact, it is our job as the communicators of our own science to clarify what we know, what we don't know, and the level of uncertainty that we have around our own data. My point is not that we can't trust our data, but it is our duty as scientists to present it carefully. As scientists, or as collectors and analyzers of data, we want to be both accurate and precise, just like that upper right bullseye. Both are components of data quality, but they mean different things. Accuracy is the degree of agreement between an observed value and a true value, like in this case, the target in that bullseye. And precision is an indicator of how closely replicate measurements agree with each other. An example from the lab is that we assess the accuracy of our analytical equipment and methods by using check standards that are a known certified concentration. And we assess the precision of our analytical methods by using sample duplicates. Chances to be slightly off on accuracy or precision are introduced at every step in the water monitoring process. We like to present our nice little means or medians, but it's always a little messier than that. Uncertainty in our data starts at the very beginning with flow monitoring. It can be very difficult to accurately measure water depth for flow rate calculations when water is flowing very fast, during flooding, or during periods where the water is changing very quickly. Also, manufacturers of the pressure transducers we often use to monitor water flow report the accuracy of their equipment. You see a typical accuracy of plus or minus 1 centimeter for this particular pressure transducer. The important thing to note is that accuracy is not perfect for any of our field equipment, and that introduces uncertainty into our data. Moving to the next, sample collection, we do know that taking samples more frequently reduces data uncertainty. Collecting flow-based water samples rather than time-based water samples also reduces uncertainty. These topics are fully explored in the next module for those of you who are going to be performing edge of field monitoring yourselves. Sample preservation and storage are also both covered in depth in the next module. In terms of data uncertainty, it's fairly obvious that if the nutrients in the water sample have degraded or changed forms because the sample wasn't preserved or stored properly, the uncertainty surrounding the resulting data has increased. Next, there's always analytical uncertainty, even in the very best of labs. Data uncertainty can be influenced by sample handling in the lab, preparation of analysis reagents and calibration standards, analytical method and equipment, and of course, the person running the samples. We talk about a number of quality assurance steps, such as duplicates, spikes, and standards, in the next module series. And finally, the last step of data processing and management can also contribute uncertainty in measured data because of missing data, assumptions made to fill missing value, and mistakes in data management. I don't want to say that happens, but you know it. There's been nice work done to actually quantify the uncertainty in agricultural water monitoring studies that can happen along each step of the process. You see, even in the very best case scenarios, there is still some error introduced for each step. And I don't even want to look at the probable error in those worst case scenarios. Breaking those uncertainties out by type of analyte, we see a relatively similar idea with this figure, but we can dig a little deeper. Starting on the left, you see the range of uncertainty associated with flow monitoring, that is the Q. And then the middle set of bars are for studies like what we do with dissolved nutrients like nitrate and tile drainage. The first bar, C, is sample collection, and looking at the median value, we're looking at about, I'd say 8% uncertainty. The next bar of sample preservation shows a median of just under 15%, so maybe say 14% uncertainty in this example. And the analytical uncertainty for dissolved nutrients is probably around 12%, just pulling that from the graph. The farthest right bar for data processing and management, you see the bar itself is pretty low, but there are some big outliers that show the potential for really increased data uncertainty depending on how you're handling your data. Just to illustrate with real numbers and just putting those values I included on the left of the screen, you would populate this root mean square error equation to get the cumulative uncertainty for the whole process. And you do that like so, with the 8%, the 14%, and the 12%. And you work through that math, ending up with 0.2 or 20% cumulative uncertainty in any given nitrate concentration value using this method. That means if I reported a nitrate concentration on a graph of 10 milligrams nitrate nitrogen per liter, that one single value really could be anywhere from 8.0 to 12 milligrams nitrate nitrogen per liter, plus or minus 20%. My point here isn't necessarily this equation per se, although I do think this way to calculate cumulative uncertainty is very cool. But my point is, one, uncertainty associated with our data does happen in every step in the data collection process, and two, this uncertainty can be quantified. One reason why being explicit about data uncertainty matters is the increasing use of models to inform policy and other decisions. Edge of field monitoring is expensive and time-consuming, and possibly not quite as glamorous as I might have led you to believe. You simply cannot rush a field study. If you have to have 3 years of monitored data, you have to collect data for 3 years, at least. And you take whatever the weather throws at you during those 3 years. This is where modeling comes in. Models allow us to simulate scenarios and conditions that we're not able to create in the field. The trick, though, is that models need to be calibrated and validated with field data. As we've been discussing, all field data has uncertainty associated with it. That uncertainty needs to be quantified and reported for those data to be accurately represented in models. There's a very famous saying there on the slide, and the version we usually say in water quality is, no one trusts the model except the modeler, and everyone trusts the monitored data except the person who collected it. That is because as a monitoring person, you see all the dirty underwear of your own data. It's good to learn early on to be honest about that. See you next time. Thanks for joining.